All right, so we are back for week 4 of Shenzhen I. Um, and I actually have this down in my calendar as diversions and digressions because this Monday night slot is supposed to be a kind of a free slot to bring up anything else I might find interesting. So last week we also did a recap of the MIT mystery hunt uh, and went over a couple of problems that I thought were fun and wanted to share with the stream. At this point, or today at some point, excuse me, I wanted to share some logic puzzles. I have a book of logic puzzles I love, has some of my favorite puzzles. And it ties in to some projects I want to do later on with theorem provers. So, if you're on YouTube watching this VOD later, you can skip ahead to that if you're interested. But for now, we need to get our. Oh, wait, that's something new. Concept spec. There's a new tile here, a new app. Steam Workshop, browse the workshop, custom specs. Oh, okay. This allows you to make puzzles and share them, I suppose. So if I browse the workshop, it brings up a page on Steam. Okay, cool. Well, that's cool to know that that's a thing. Anyway, back to our email. I wanted to do a quick recap on the 2 problems I looked at last week, just to see if I see any optimizations. I think I did pretty well here. It was an unknown optimization device. Right, this was the distributed autonomous corporation, the AI corporation, requesting a part for a plutonium ore mining. And no questions asked. We like, okay, we'll design that for you. Okay. This was pretty simple, like conceptually. Let me pull up the manual. Like it's just so we remember what it was. Here. Based on like XY coordinates, we're supposed to have different values. And now this is really easy, if else, whatever, in a high-level programming language. Here, our conditionals were a bit different. So I had to do this, like, test all the conditions together. And this is the, like, if we are in the inner box. And otherwise, we jump to the outer case. And you have to do these jumps because we can't really nest conditionals. So I found something that worked. It barely fit in there. And it's a pretty tight solution, I think. There's not a lot to improve. So I won't look at this too long. If I trim down that one line of code, or I guess that's not more than one line of code, that'd be cool. And someone did it in 6 instead of 8. But otherwise, I'm pretty happy with this. Nothing comes to came like immediately to mind as far as how to optimize this. Okay. The 3 kingdoms tokens. Oh, I was also pretty happy with this. Yeah, no need to work on this. Yeah, our inputs here are tokens being added in. And we have a check for each of those token values. Right, so we sum up, we have a loop, we sum up those token values. Um, and then, let me see. At what point do we... I can't even remember at what point do we say like it's time to give change. After a sufficient number of coins. Okay, yeah, as soon as we hit over the price. So yeah, we're in a loop here adding up until we hit this 16 coming off of the X0 right here. And then we calculate the change, send that over to this machine, which then sends out the 5 and 1 signal, while this one, in the meantime, sends the signal to the bell. Okay, and we're able to use the new gen command. That's an undocumented command. Probably there's a space here to use the... There's another undocumented command. There's like an @ for initialization code that only gets called once. I don't think we're ever really initializing anything here, are we? I guess we could initialize the price here and not constantly read that over. We could read that into data. But I don't think there's really any point in that. Right. Yeah. Okay, cool. So, happy with my first designs for both of those. Let's get into new stuff. Email. Shenzhen I, say cheese. Okay, remember when I said I only had one thing to complain about Westerners living here? Well, I have another one. So sorry, but here I go. I'm complaining about cheese. That's right. Talking nonstop about your precious, precious cheese and how they don't exist here. Definitely not in the quantity, quality, and variety that they do in France or Wisconsin or wherever. Well, it might be hard to wrap your head around the fact that an entire civilization and one of the top culinary traditions in the world was developed entirely without curdled milk solids. But it's true. In fact, like, isn't like 2/3 of the world lactose intolerant? It's true. It happened. Which is not to say I don't like cheese myself. I do. Late night, you might even find me at McDonald's on Shannon Road eating cheeseburgers like the gluttonous young modern global citizen that I am. I am just saying there's plenty of good and legitimate food that exists without cheese, and it's not something you're gonna die for the lack of. Yeah, I'm agreed here. Anyway, when you take a picture, don't say cheese in China, because why would we say that? You say eggplant. You heard me. Cheesy. Cheese. I'm gonna assume it's cheesy. Say it right, and it sounds kind of like cheese. Cheesy. I'm gonna assume it's cheesy, but maybe I can look that up. Well, thank you, Tilly, for the email. Sandwich assembler. Product, personal sandwich maker. Okay. From Joe. Yo, dogs, I was out drinking last night and realized, you know what Americans love? Sandwiches. Am I right? Americans can't get enough sandwiches. I sketched out a quick design for a patriotic sandwich machine where you put in white bread, bologna, mustard. It could play a song when it finishes. More details come later when I'm less hungover. Maybe. We're not actually gonna do that, are we? I have a keypad that will work for this, but it uses normal XBus, which will block until a key is pressed. You will figure it out. Okay, so we're actually doing this. We're doing Joe's hangover idea. All right, G, we'll do it. Okay, so we have a keypad, XBus connected to this keypad, and you have an order, I guess. So bread, meat, cheese, and mustard are simple outputs connected to the mechanism that dispenses those ingredients. Bread, meat, cheese, and mustard. Flag is a simple output connected to a motor that raises and lowers a small American flag when a sandwich is complete. Lovely. And when a value is available from the keypad, read it and dispense the sandwich using the information in the following table and the verification tab. Okay, so 1, sandwich time. We dispense a sandwich with meat, cheese, and mustard, in that order, I suppose. So 1, bread, meat, cheese, mustard, bread. Cool. 2, hold the cheese, dispense a sandwich, but don't add cheese. 3, extra mustard, dispense a sandwich with extra mustard. Okay. Well, I could just do a sandwich instruction and then add conditionals for the cheese and the extra mustard. So why don't we start with that? And then the flag always goes up when it's complete. Let me just look at the flag information here. The flag goes up for 3 seconds. And now we have the gen command, so a lot of this will be easier. Okay, so to make a sandwich, we, oh, wait, first we have to figure out what we're sending where. Let's wire this together. So I could use a DX300 here for the bread, meat, and cheese. Will a pulse work properly over the DX100? I want to test that real quick. So let's say we were just doing gen on X3. We're just going to go up for 2 seconds and then down for 2 seconds. Down for 4 seconds. That's our loop. Must be a simple IO pin. Oh, okay. Right. Well, okay, we won't be able to use gen that way, but let me just try something. So let's do, we'll just send some individual commands. So we'll play around with doing it this way anyway. So move 100 to X3, sleep for 2 seconds. Move 100 to X3, sleep for 4 seconds. Right, and that will always light up this one. Oh, no. We have to move 0 to X3. Light up none of them. And simulate. So that's bread. Oh, we can see it in the little machine graphic here. I'm hiding it, but you can see it dispensing the bread. Cool. All right, so if we're gonna want to minimize number of pieces, that's gonna have to be the way that we do it. Then we can send gen commands over this. Why don't we do that for the 3 ingredients? Because those will all happen just like once or maybe not at all. The bread's gonna happen twice. And the flag always happens. So P1 can be bread. X3 can be the DX300. Will I have enough space though, is what I'm concerned about. So we start by doing gen 100 on P1. or sorry, not gen 100. We're gonna move 100 to P1, sleep 1 second, move 0 to P1. And then we, oh wait, no, P1 can be gen. So gen P1, we're gonna pulse out 100 for 1 second. So 1 second and then rest 0 afterwards. And then we have this. This is for beat. I'll leave a comment. So sleep 1. And there's not going to be a sleep afterwards, so that's nice. Then we move 0, 1, 0 to X3, and that's going to be cheese. And then we sleep 1, move 0 to X3. I guess we don't need to move 0 to X3, do we? There, a sandwich. And this is all going to be gated on input, so we're going to sleep X on the X bus. Sleep 1, do the cheese. Sleep 1, and then we're going to do the mustard. 0, 0, 1. And then we're going to do the bread again. Gen P1, 1, 0. Move 0, 0, 1 to X3. That is our mustard. And then after all that, we generate a pulse for the flag of the United States of America. Pretty sure this is violating flag code. Gen P1 3 0. Okay, so that fits pretty nicely. I don't think we have to worry too much about... Well, it is making sandwiches. We have that. I'll show you the machine. It's making sandwiches on top of sandwiches. Okay, now we need to gate that on the input. So we can just save that to the data. So sleep X, we're waiting for X0, which, yeah, we'll connect that. And then let's move X0 to the data register. Okay, so now it won't make the other types of sandwiches. Oh, what's going on here? P1? Oh, the flag needs to be on P0. Okay. Let's take a look at that. Great. My bread came too early, my second bread. So after the mustard, let's look at this here. After the mustard, oh, we forgot to sleep. Sleep 1. And then we need to clear out those 3 ingredients. So we're gonna move 0 to X3. And then send our pulse. Oh, we are running out of space. I take back my words. I'm eating my words. Okay, great, that's good. Now, if data is 2, then mustard should last longer. So we can have a second sleep command. So that's 2 lines of code. We need 3 more lines of code because we need to gate the cheese command. Let me make this more concise. I suppose we could have two chips. Like, all of this logic for the meat, cheese, mustard and go separate. And then the stuff that's always happening, so the bread, whatever, the bread and the flag can be on another small chip. I'm gonna do that as, I'm gonna copy paste that and do that as a new design. Because I don't know, maybe later on we'll figure out how to remove that or fit that all onto one chip. It probably involves using, well, the thing is we can't use multiple gens because we don't have multiple basic IO chips. Okay. So controlling this DX300 here, this tri-split, we're gonna have one of these. And you know, let's just take a look at this code here. How many lines? We're using 2 lines for each of these. The gen ends up using 1 line. Yeah, okay. So this is gonna wait on its own X bus. And its X output is going to be connected to the splitter over here. So we're gonna sleep. Hey, Sparkly Dark Matter, good to see you too. Always good to have you. So this here is a personal sandwich maker. It makes sandwich. This is for the Americans. It makes sandwiches and then raises the American flag when it's done. It has 3 whole different recipes. Sparkly Dark, do you like logic puzzles? Because that's what I have as a digression tonight. At some point, I'll bring some out. So we can move. We're just gonna copy all of this. Actually, the meat, cheese, and mustard. Patriotic panini has excellent alliteration. All right, so we're gonna sleep on the X0, wait for a signal. Then we do meat, cheese, and mustard. Oh, okay, my reason for moving this to a second chip is because I wanted to add in conditionals. There's a conditional for the cheese and for the mustard, but there's no room. There's no room if I'm gonna do it that way. Eesh. Okay, fine. You know what? We're gonna start with 2 big chips. We start with 2 big chips, and if we decide later that we can downsize something, we'll do that. That's fair enough. The book of logic puzzles I want to pull from, it's my favorite of all the like math logic puzzle books I've read, but I have not finished it because it gets really gnarly by the end. And it's a book of logic puzzles. It's secretly a book about self-reference, about fixed points, and about combinatorial logic, which, if you're not familiar, it's basically lambda calculus without bound variables. So it's like proto assembly lambda calculus. Okay, so same kind of thing here. Sleep on x0, and then we'll move x0 to data. Okay. That should work. Now, x0 here is supposed to be our whatever our keypad input was. And based on that, we might not always do meat, cheese, and then mustard. So let's see. In the case of mustard, I'll add a conditional here. We're going to sleep for an extra second before we move 0 to x3. So we're going to test equal on a data register. If it is 3, then we sleep for 1 second. Howling Fan Tods, you made it. Hey, good to see you here. You're bad at combinatorics, but Prologue is one of your white whales. Fair enough. I've never done Prologue. The closest I've done is Mini Canron, which is logic programming-ish. They actually call it relational programming. You can use it in much the same way. From itertools import permutations, that is exactly how I used to code in Python before I moved to Scala. I love the itertools library. And func tools. I always use those too. Okay, so we sleep an extra second to continue pouring mustard onto this sandwich. What's the other condition? Cheese. Dispense a sandwich, but don't add cheese. So this whole cheese block here is going to be gated based on if it's 1 or 3. So we get test equal 2. So we're going to test if our data is 2, and that's to hold the cheese signal. And in that case, wait a second. Yeah. In that case, these two become negative. Okay. I think that works. How about a warm-up logic puzzle? Okay, this is a really easy one. It doesn't really tie into the others, but it's a warm-up. Okay, so there's a certain flower garden. Every flower is either red, yellow, or blue. And all 3 colors are represented. So a statistician once visited this garden and made the observation that whatever 3 flowers he picked, at least one of them was bound to be red. Another statistician visited and noticed no matter which 3 you pick, at least one was bound to be yellow. Now, a couple of students heard this, and student A says, well, then it follows that no matter which 3 you pick, one should be blue too, right? But the other one disagreed. So which student's correct here? Does it follow? Does it not follow? And if not, why not? Okay, so back to it's storming in Texas, so there's power outs. You know what? I think Texas and Maine are both like top 3 for states with power outages. Maine has so many trees. Every time we have a storm with like lots of wind and trees fall over, all the power lines go down. And we've had like 2 feet of snow in the last 24 hours. I spent at least an hour running the snowblower outside earlier today. But I've had power the whole time, so that's good. I've had power and internet. That stream hasn't crashed yet, so knock on wood. But yeah, are you worried your stream might go down tonight, Howling? Over there, it's all ice. Fair enough, fair enough. Well, it's good to have you here then. Okay, so we've got the innards of the sandwich logic here. Um, and it's a lot, even though it's simple. I wish I could write that in less lines of code. So now here, it's just gonna be the general sandwich. I'm gonna hook this up to the bread, and I'm hoping I can do this in just a small chip. X1 can be sending the instructions over to the, what'd you call it? The filler? We're gonna call this like the filler module. And we can copy from over here. So we're gonna sleep on X0. X0 is gonna be our keypad input. SLX on X0. And then we're gonna pulse for 1 second to the bread. P110, there we go. And then we're gonna send the command to the innard machine, the filler machine. So we're gonna move X0 to X1. And then after the filler machine is done, oh, we have to wait. Okay, so we're gonna move X1 to null because we're gonna wait for a signal here. Or we're gonna sleep on X1 rather. SLX on X1. So after this is all said and done, the filler machine, we're gonna move null to X0 to send a signal back that the filler machine is done. Great. And then we do the last piece of bread, gen P110, and then we raise the flag of the United States of America for 3 seconds. So gen P0 for 3 seconds, 0. And I think that is that. Part not sleeping, blocked on right. Move null to X0. Oh, okay, we actually have to do something with this. So instead of sleeping on X1, I'm just gonna move X1 to null. Part not sleeping, blocked on okay, fine. We're gonna sleep X on X1, and then we're gonna move X1 to null. There we go. We figured it out, I think. Okay. Hold the cheese, extra mustard. Hold the cheese, extra mustard. Plain old sandwich. Okay, we've got it. Ah. Hey, and the stats aren't bad. Production cost firmly average, so I guess a lot of people took a similar route. Power usage is a little bit high. 1 lines of code. That's concise. That felt like a lot of lines of code. Okay. Anyway, you're saying your ruler measured 11 inches. You need a small power bank. Yeah, it's always good to have. I have here a 1K kilowatt hour battery. It has like another 1K attachment. So I have 2 kilowatt hours of battery, and I actually attached my whole workstation to it. So if the power goes out during the stream, like I can still keep going for a bit and at least tell people, hey, I'm out of power. And I don't know, 2 kilowatt hours, let's say I'm using 300 watts, that would still last 6 hours. I'm probably using like 500 watts. So let's say 4 hours. So that's not bad. And my computer also has cellular data, so if the internet goes out, which it shouldn't because it's fiber, I'll probably be fine. The worst part of the snow you got is it's really cold, so it's all powder. Yeah, yeah. Right, cold, dry snow. That's kind of what we're getting here too. One Fahrenheit. Jeez. What is it here in Maine? It is -1 Fahrenheit. Hmm. Most of the black hours you've seen resolve in 2 to 4 hours. Oh, that's good. I've had last year I had a blackout that lasted for 24 hours easily. We had to get the generator running. Um, don't tell anyone this, but we used a suicide cord. Are you familiar with those? So you backfed the generator into the. You shouldn't do this, because like you could kill people that are working on power lines, uh, if your house is connected to the power grid, and you could kill yourself. Yeah, male to male AC. Yep. How it works? Well, should I be saying this? You can't even buy them. You have to make them yourself. So you have to wire the cable together so that you can, you know, the generator has a plug, and you plug it into an outlet in your house, and that feeds the power into your. Uh, I was terrified of it. I was very careful with all my steps, and how I handle the wires. But don't do that. People burn their houses down and kill themselves and stuff like that. Yeah, you should be terrified of electricity. And especially don't do that if you don't know how your house is wired. uh, every now and then I see clips of electricians commenting on something in their house, like something that they're seeing in an inspection, and they have had this voiceover of someone saying, "Hey, who did your electricity? Oh, my nephew did it. Uh, oh yeah, when did his house burn down?" And she's like, "Oh wait, how do you know his house burned down?" Uh, okay, results for the sandwich assembler. I'm sorry, I'm really trying my best to come up with good ideas, but obviously, as you pointed out, I have more work to do in that area. Oh, hold on. Is Joe our product manager? I think Joe is our product manager, or like our head of product or something. Um, please give me another chance. I mean, this guy was doing this on a hangover, and it was an idea he had out drinking. So I think like three of his ideas have come back from like when he's been out drinking. I swear I'm going to reduce my efforts, redouble my efforts, and work extra hard to create a successful project for you. I promise. Please disregard the previous message. Hit the wrong button. Did he like reply to the wrong email or something? But here's the thing. G just like went with it and was like, okay, here's your here's your numpad. Have at it. So I mean, it's on both of them, right? Uh, you'll admit you have a death plug in your house which randomly kills electronics. Yeesh. You've mellowed out on electricity when you learned that house electricity isn't considered high voltage. Carrier lines and substation stuff. That's terrifying. Fair, fair. At least it's warm in there, exactly. Um, but let's go back at the introductions. Okay, so this is the CEO, and Joe Haitao is the product manager. Okay, and who is Ji Zhang? I'm the chief staff engineer. Okay, right. Is it true that if you partly plug in the cord and touch the metal, you get electric? I would think so. Why not? Well, hold on. It might not be because like you might need to plug it in all the way in order for the connections to actually reach. I don't know. But certainly, I've heard people complaining that like American plugins aren't as safe as like European or elsewhere. Ground is not always ground either. Like sometimes it's just wired to I forget, but it's not always wired the same way. So there's a lot of stuff to be careful about. That's all I know. I'm no electrician. I know you need to be careful. Um, let's look at another one. Yeah, like sometimes ground is neutral. Okay, carbine target illuminator. We have a deal to create a highly portable infrared targeting device that automatically switches entire modes based on range. At long range, the aiming laser is on. Okay, what kind of device is this? At mid range, the aiming laser switches to half power and turns on a 20-degree flood emitter. And at close range, it switches completely to a 60-degree flood. I've placed a copy I've placed a copy of the table on your desk. As a mounted add-on for any type of carbine weapon, it has the potential to do very well across government and law enforcement agencies. I'm going to nope right out of this one if none of you mind. Okay, so it's on us to design the laser scope slash illuminator. We've been doing a lot of government work, haven't we? Okay, so we have radar out, radar in. Radar out is a simple input connected to a miniature radar unit that indicates when it fires a radar ping. Okay, so these are radar pings. Radar in is a simple input connected to a miniature radar unit that indicates when it receives a radar ping. Okay, so this is when once it receives. If I receive, I guess then we have to look at the length of time, measure the delay. Okay, measure the delay. Laser is a simple output. Okay, there's flood 20 and flood 60 are also. Okay, so there's 3 output states. We don't really have to worry about anything but sending pulses there. Or actually it's a state, so just like one of those 3. Probably we'll like stick a DX300 on there. And then we just send a full state to this one here. The tricky part's going to be measuring the delay. I'll have to think about that. Measure the delay between the start of radar out and radar in to determine the range. Control laser flood as specified in the carbine target illuminator. Okay, so we have to look up this up in the manual. Carbine. And I'm going to check here. Carbine. Their rifle. I think I'm pronouncing it right. Replace this page with the engineering notes section. No, that's not right. Here we go. 1 to 2 time units is going to be the 60-degree flood. 3 to 4 is here, and 5 to 6 is 100. 5 to 6. Let's read the product manual here. Don't let your operators get caught fiddling with rangefinder settings at the wrong moment. Today's aiming devices for individual carbine weapons often feature complex illuminators with multiple switches and dials, which can be difficult to operate in the dark or worse during an engagement. The PP221 eliminates these issues by automatically snapping to 3 predefined settings optimized for common engagement distances. Okay. Close quarters, wide variety of urban environments, and outdoor use. 1 to 2, 3 to 4, 5 to 6. Okay, so what we could do here is we could sleep and add 1 every second, and then we check the radar input, which I think are basic inputs. So radar out is a simple input. Yeah, and radar in is also a simple input. Okay. So current plan, actually we could just add every 2 seconds. Every 2 seconds we just check if it's on or not. And depending on when it is, this is actually pretty easy. So let's pull out a small chip here. Will that be enough? Probably not. Let's do a big chip. So we'll wire X3 to our splitter. And we have radar in, radar out. So out will be off of P1 and radar in will be off of P0. Okay. So we're gonna keep checking P1. So test equal P1 to 100. And in that case, we're gonna jump to measure. We'll call it time. Otherwise, we're gonna sleep 1 second and just jump back to the start. Which I'll just note with an S. We can put that on its own line here. Great. In fact, what I might just do here is put minuses there. So if it's not, we jump back to the start. We don't need to jump to time. Okay, and now in this case, we're timing things. So we're gonna sleep for 2 seconds. Let's look at the verification tab. So radar out. In this case, 1 to 2 seconds. I think we need to sleep every second. Maybe we just measure the whole thing. Let's just measure the whole thing. So we're gonna sleep for 1 second. And then add 1. And we can jump to, we will have a loop, we'll call it time. And we're gonna test if our radar in, so P0, if that is on, or if that's off rather, then we jump back to time. Okay. Now this is a little bit different from my initial idea, which was to just wait 2 seconds and check and move from there. So I'm using a loop instead. Which, I don't know, it might still be. This is probably better because we do have to check each of the 6 seconds and not just 1. But that does mean we also have to branch on what comes out of accumulator afterwards. So we'll test if it's less than 3. Test less than 3. In that case, oh wait, test if accumulator is less than 3. We're gonna move, well, we do multiple things. Right, we'll do laser. Laser's potentially gonna happen at 50%. Oh, laser cannot be plugged into this. So this is not a good plan because laser can be 50%. Okay, well maybe we split this up across 2 chips. So after all of this is done, we're gonna move ACK to some sort of output. Move ACK somewhere. And what I want to know is if that can fit on here. Okay, that can fit on a small chip, so we can use 2 small chips for this. Flood 20 and flood 60 are basically just on off, so they can still be connected to the X300. Which leaves us with this connected to a basic port. So we'll need a basic port. I think we just get one of these here. So P1 goes to the laser, and then X1 can just go to the splitter over here. And that can wait on X0. Ish, we don't have a lot of space here. I'm gonna wire this a little bit differently. Okay, so X1 goes to the other chip. P1 is still going to be radar out, and that's radar in. So we're going to move accumulator to X1. All right. Oh, we lost a command here. So I'm going to need more lines of code, so the labels can go on a line of code, so I can do that. And sleep 1 as well can go on the time command. And if it is 0, we jump back. Well, hold on. If it's 0, we're going to jump back to time. Jump to time. Otherwise, we move ACK to X1, and we go back to the start, which looks for a pulse. We might as well add a sleep 1 here at the end. Okay, that will do us. I just kind of want to test that separately first. Oh wait, that's an X bus. Okay. We can find another way to test it. So here, we're gonna sleep on our X0, and then move X0 to our accumulator. So now we do our test on this. So test less than. So if our accumulator is less than 3, oh, we might need a big chip for this. We move 100 to P1. we move 0 to x1, turns both of those off, right? And then if it's greater than... No, hold on. I did that wrong. This is the one where it's far away. So we're actually going to test if it's greater than 4. Yeah, we'll test if it's greater than 4. And we turn on the laser. And then we test if it's less than 3. In which case we do the flood 60 and lasers off. So move 0 to P1, and then we move to turn the laser, to turn just the flood 60 on, it's 0, 0, 1. 0, 0, 1 to X1. And it turns out we need a big chip for this, so the big chip we will use. So copy paste that right into here. Let's see if we could still use X0 in the same spot. X0 and P1. Now this becomes X3 instead. Okay. And in any of these cases, we would jump back to start. Right? There's no need to do other tests. Yeesh. I'm using too many lines of code. So otherwise, we move 50 to P1. Lasers at 50%. And we... I probably can remove some of those jumps. Move 50 to P1. And we move 100 to P2. 100 turns on flood 20. Move 100 to X3 out there. Okay, and we go back to start. So these two can actually just be a minus, and we can remove this jump to start. I think in this case here, we do need to jump to start. Because otherwise, yeah, we can't really nest conditionals. Let's give that a shot. It feels suspicious. I feel like something is wrong. Okay, so there are a few times when we had the thing wrong. So in this case, the second pulse, probably we're getting the actual pulse wrong. Oh, and also, hold on, before we do any adding, we have to set it back to 0. You know, we didn't really need to do the sleep here. So we're gonna move 0 to accumulator. And it basically starts with a potential sleep or a sleep here. Wait, it's gonna start measuring again without any sleep. No, I think it will go to sleep. Let's try it. Are we blocking? Okay, there we go. Oh, hey, that's just it. That fixed it. So you can see the oh wait, what's going on? Let's keep stopping. Do I have like a breakpoint or something? I shouldn't need to keep clicking this. It should just run the simulation, right? It's acting like I'm hitting advance, sort of. Okay, reset, hit simulate. This one's currently sleeping. We sleep one, add a second, then we check if it's time to stop before jumping back. And then eventually we will always move the accumulator out and move 0. I don't know what's wrong with this though. Oh, no. There's not clearly anything wrong with it. It just pauses. Is that a bug in the game, or have I done something to break this? Well, here's the thing. Every time I do that, it doesn't always go the same distance. If I put it into like some sort of race condition deadlock, like my sleep here is definitely a little bit sus. Or like my lag of sleep here at the very end. Okay, there's one very quick way to debug this, and that is putting this into a big chip where I have room for that final sleep. Okay, X1 becomes X3, P0, P1, yada yada. Okay, at the end of all of this, we're gonna sleep for 1 second. It's still randomly pausing. And it's always at this state here on the right side. Or is it here when this is really short? This is 0 seconds. Let's see which cases do that. Here, that should be 1 second, right? I'm not sure whether to count this as 1 second or 2 seconds, to be honest. But whatever I chose seems to work. Out in, it pauses here at the 0 second. Pauses here at 1 second. Back to the start. Oh, okay, it was a bug in the game. It must have been a bug in the game, because now it just works fine. Okay. And you know what? I don't think we need this sleep. I'm gonna delete that. Let's run it again. See, as a programmer, I'm trained that it's never like the compiler. It's never the system. But in that case, it was. So we can move this back to a small chip. Uh, okay. Get rid of that. Oh, actually, this is the code I want. The leak code special. Fair enough. I've not really lived with that. Cool, he got it. And firmly average. Some smarty pants here did it in 7. Our usage is perfectly fine. Mine's a code. I'm happy with that too. When they get this small, I know that's going to take me a while to optimize to the point of getting that. Okay, okay. Yeah, I don't really see much of a, like, it'd be really tough to cram this one onto a small chip too. Maybe there's something you could do that's really clever, merging the laser stuff or whatever. Like add 50 in certain cases, or I don't know. But I'm content. Cool. We did it. We made some kind of thing that goes on another thing that's made for killing people and helps them kill people ever better. Yay, go us. Carl really does not like this. Carl, I understand your concerns, but let's take this offline. Very corporate answer. The thing is, who are we making this stuff for? Okay, so let me fire some logic puzzles at you. Because there's a section here that is really cool. And it's a bunch of logic puzzles that have been turned into only it's nice because you can kind of brute force them. All the answers are 3-word answers. So I've got puzzle. We have triplets, and they're all identical. You can't tell them apart, but 2 of them always tell the truth, and 1 of them always lies. So they are Taylor, Tyler, and we need faults. Frankie. So Taylor, Tyler, and Frankie. Taylor and Tyler always tells the truth, and Frankie is always false. One day you meet one of them, and you wish to know whether it's Taylor. You're only allowed to ask one question, one yes or no question, and the question may not contain more than 3 words. What question would you ask? It's got a bunch of variations on that. I like him because you can kind of just like think of what are some 3-word questions. How do you figure out if this is one of the truth tellers, specifically Taylor? Are you Frankie? Well, Frankie would say no, and so would Taylor and Tyler. I can let you chew on that if you don't want spoilers on the puzzle itself. Actually, there's a fun one that we can play as a game together. Does 1 plus 1 equal 2? Well, if they say yes, then do you know which one is Taylor? Do you know if you're talking to Taylor? Because Tyler also tells the truth. But 1 plus 1 equals 2. I think that counts as 4 words. No, that's 5 words. No, that's 6. Does 1 plus 1 equal 2? That's 6 words. You're double your budget. So the haunted doll. Oh yeah, we're not trying to find Frankie. Finding Frankie is easy. You have to find one of the 2 truth tellers. Okay, so haunted doll. You keep a secret. Haunted doll project. Hey, so I was doing some research on the internet. It seems that if a doll is a haunted doll, it brings way more interest. Okay, haunted dolls that get caught on a live stream are almost guaranteed to go viral. So what if we took some of the dolls from a factory around here and put some parts in them to haunt them, then then distributed them along with normal dolls to toy stores? Oh my god, haunted doll. So we're gonna make a deal with a company and be like, hey, we're gonna haunt some of your dolls so that your doll company goes viral and just put them on the shelf. Is that the plan? Joe, are you serious right now? It's actually kind of smart. But Joe is pretty unhinged with his ideas, isn't he? This is brilliant. I love this. I found some appropriate sound effects online. I think Sinister Giggle and Blood Curdling Cry are the best of that bunch. Now we just need a random number generator, preferably a haunted random number generator. Uh, and Zhang pipes in here. We have some unmarked chips from a long time ago in storage. The original purpose of the maker is unknown. Seems interesting. I put some in the prototyping bin. Perhaps this part was created by a ghost shift. This is just some joke humor. Well, thank you for explaining that it's a joke. Perfect. Let's go terrify some live streamers. Why do they call them live streamers? Like people that stream their lives as opposed to like live streamers? I don't know. Okay, I know you're working on that puzzle, but I've got one that's kind of fun to play as a game with a group. So, um, you've got a game show, and I'll role play the host. And basically, there are 3 prizes here: A, B, and C. Um, C is kind of a booby prize. You don't really want it. A is a really nice prize, and B is also a nice prize. But like you want A, you want prize A. um, and to win a prize, you have to tell me a. Yes, you ask one question and to identify who you're talking to. Right. So Taylor, Tyler, tell the truth. Frankie is always false. You meet one of them. You wanted to know if it's Taylor. One question, 3 words. A game show. So A, B, C. A is the best prize. B is okay. C is not really a prize at all. Here's how you win a prize. You make a statement, and if it's true, I'll give you one of prize A and B. If it's false, I'll give you prize C. So if you want to get prize A, what kind of statement can you make? So if you want to play that, you can make a statement, and I'll give you a prize as a way of checking your answer. And let's work on this haunted doll. So we've got we've got we've got an actual haunted ship here. Um, so this is our random number generator. Random is a simple input connected to a random number generator. Speaker is a simple output connected to a miniature self-amplified audio speaker. When the value of 1 is randomly pressed, play the sinister giggle sound effect. Otherwise, play the blood-curdling cry sound effect. Look in the supplemental data section of the manual for the audio data that Carl found for these sound effects. If it's true, yeah, I can choose A or B to give to you. If it's false, I can choose C. So you only get one prize no matter what. But you have to make a statement, and I get to choose the prize. Okay, so we gotta open the manual here. Where is it? The creepy Dark Lord 555's creepy sound effects page. This page is designed for Internet Explorer 3.0 or better. You are the 1792nd visitor to this page. You have found yourself in a dark wood, in a huge forest with no beginning or end. What is that noise? Before you know it, the darkness has taken you. I like this old internet page. These sounds were recorded and modified by me, Dark Lord 555. They are free to use. You can use these sound effects to scare your little sister or whatever else. I don't care. This is such a 90s webpage. Explorer 3.0? Is that gonna be like 95 or something? So Sinister Giggle. Oh, we play that whole pattern? Blood-curdling cry. Okay, so we have to play that whole pattern. There's an actual URL here. No, wait, I'm gonna check that URL on the side here. webhomes.code.ee. Is that even a TLD? webhomes.code.ee. Nope, site does not exist. Okay. Well. We'll probably have to have... oh, do we have read-only memory here? Can we use that module? Yeah, great. So we'll just put them into here and play them. We need Sinister Giggle and Blood-Curdling Cry. And let's see, I'm gonna keep this cover. Oh. Okay, we can do this. Sinister Giggle. 100, 80, 41, 14, 14, 41, 69, and 74, 54, 27, 19, 40, and 75. Followed by a 0. Oh, perfect. I could use 0 as like my terminator for that. And we need Blood-Curdling Cry. (16, 36, 42, 14, 10, 58, 100, 76, 26, 28, 70, 80, 42. Okay. Random simple input, and once it hits that particular input value of 1. Then we play that to the speaker. One sinister giggle. Okay. Let's get a big chip here. And this, I don't even know what kind of input that is. So is it X? Does it also work on P? I'm gonna assume it's a basic input and just check it every second. Right. If it was an X, could it actually go... No, the pin type has to match. I'm just gonna move P0 directly to P1 to see how this chip works. Move P0 to P1. And... and then we'll just sleep in a loop. Oh, and this part needs to be on the board too. There we go. So it is not moving anything out. Am I missing the input somewhere? Random simple input. Is this really the input chip? Okay, what if it's X? So we're gonna move X1 to P1. Oh, sorry, X1 to P1. Part not sleeping, blocked on read. Right, blocked on read because it's not an X. Alright, well, we assume that then. I just think it's weird that our output is not changing. I'm not sure I know how to use this chip. Okay, let's move P0 to the accumulator so that we can inspect it. And then in a separate step, we'll move the accumulator to P1. Always getting zeros, so maybe we're reading the wrong pin. Okay, we'll try another pin. Aha! Okay, that's it. We're using the wrong pin. Oh, whoops. Let's go back to there. Okay. So we're going to test if it's equal to P1. Or sorry. So we're going to test if P0 rather is equal to 1. In which case we'll play this out here. So we have... How do we want to connect these? Put that on the very edge. And A is the address register, so we don't really need it. D is the data. We might need the address register. It's there if we need it. And data is on top, address is on the bottom. I don't like not being able to see the pins, so we'll do it this way. You will receive prize A. False. I give you prize C. You didn't know you were going to make a false statement, did you? I do enjoy playing this this game, exactly for that. Oh, I forget which is which. Let me pull up the manual here. The one that starts with 100 is the Sinister Giggle. Okay. So we're going to test if P0 is equal to P1, or if P0 is equal to 1. And if so, we're going to play the data from here. So we have a loop. We'll just call it Giggle. So let's have Giggle. And we're going to move x0 to P1, sleep 1 second, and then jump to Giggle. Conditionally, logic puzzles melt the brain. I feel that. I did give you prize C. No, it's true that I gave you prize C because you made a false statement. You said you will receive prize A, but that was false. So I gave you prize C. Okay, jump giggle is conditional. And basically, if it's not 0, so we're gonna test equal, oh wait, data pin. So we're gonna move x0 to data first. And we don't want to play a 0 at the end of this, do we? It's fine to play a 0 at the end of this. No, the baseline is 50. So we're playing 50 all other times. Okay. So first we check the data. Test equal data to 0. And if it's 0, we need to escape out of here. We're gonna jump to done. Otherwise, we're gonna move the data to P1 and then jump back to Giggle. All right, that's all nice and all, but it might be too long. Right, like done on its own. I hate having to do this on 2 chips because it's all wired so nicely right now. Okay, so once we're done, we move 50 to P1, and that's it. We go back to the start. Wait, we need to sleep. Sleep for 1 second. Okay, great. This definitely won't fit on here, but maybe I could at least... Like, maybe I can fit both of them on one chip. Let's see. Like both of the audio loops. So let's say we have giggle. Actually, I don't like having both of these. I have to have two jump statements. Oh, this jump to done would be if that's true. We get away with not having two. See, if I could gate this at the end. The thing is, we performed a test here. If we could put the test at the end, that'd be great. But I'm not sure that we can do that. But in any case, let's copy paste that, and let's add a done. So we can put both on one chip. We have some out signal here. But how do we choose between these two? So one's giggle, the other is laugh. No, cry. And in this case, we move the other register, so this is going to be X2. And we jump back to cry. So this whole thing can be gated under sleep X on some input, but then we'd have to branch based on that input to one of these two. Which doesn't really work all that nicely. Okay, we're gonna make a duplicate, and I think we do have to start. We have to use multiple chips. So let's just start by making it easy. We can always optimize later, or not at all, I don't know. So, what we could do is just like pack each of these onto an MC4000. So here's the giggle. It's going to be our 1. And we directly connect it to a chip that just reads it. Yeah. And in fact, do we even need... No, we do want to use a P1, the P output. Can we connect two different things to the same output though? I'm not sure if we could do, let's see. Let's see if that works. So let's get 2 of these chips. We'll connect P1 of both of these. Okay, I think that potentially works. So here the data goes to x0. You do not know what spoilers I need to be mindful of, but you're now being aware of them. Well, fair enough. If you don't have any spoilers, then nothing to worry about. But I am solving a puzzle. It does have a solution. In this case, it's kind of hard to spoil this one. Welcome, by the way, ankle biter. Okay, so we'll do this the expensive way, and we can just have a chip per audio file. I need to put the piece in the right place. Well, I appreciate that advice. See, that's the kind of light backseating that's totally okay with me. You're like helping me out without actually spoiling it. Okay, so we have a giggle, and then we have a done. And when we're done, we'll just communicate back to x1. And I'll have like a master chip. And the master chip can handle communicating with the random and communicating with those two. And I guess it should also do some... So I could have the master chip handle the 50, the default 50 output. And it was the top signal here, wasn't it? Let me just test this. Move P0 to P1, and then sleep 1 second. Oh, we don't have a data, but we do have an accumulator register. I'm just gonna delete that for now, so I could test this here. Nope, it's not that one. Maybe it's this lower one. Okay, the lower input is what we need. I've tried flipping all sorts of doohickeys and I still can't solve this problem. Okay, so those are both connected to an output. We jump to giggle. Maybe we can sleep on x1. So sleep on x1 and then move x1 to null. And when we're done, we move null to x1. Send a signal right back. And since this is generic, we can just make this play instead of giggle. Maybe we'll leave a note to ourselves that says giggle. Same code here. We'll change the comment though to say that this is our cry chip. Alright, so we can connect one there. Oh, there. And we'll need a couple bridges to connect the other one. Okay, how's the circuit design? This isn't too bad, is it? That's very reasonably wired. It is a little sus that 3 of them are all connected to the speaker. But we'll manage. So we're just gonna constantly, I think, test P0. Test equal P0 to P. We check if it's 1, I suppose. And if it is 1, we're going to giggle. So we're going to go to the upper one here. Move null to x1. And then sleep on x1. Then move x1 to null. Right? Otherwise, if it's 2, we're going to do the other chip. Right, we cry. P02. This is how you feel soldering DIY PCBs. Wire over wire. I've never soldered any. I've played with breadboards and like just directly connected wires on like small circuits. And honestly, that was pretty fun. Maybe after this, I'll get into Arduino. So here we have something very similar. We move null to x0. Sleep on x0. And then we move x0 to null. And otherwise, we move 50 to P1. And then we sleep. We need to sleep, but we're short one line. And we can't fit a big chip on this. I guess we could if we like really move stuff around. Well, crap. Right, so this chip fully blocks while the other 2 chips are running. So they'll never all send a signal to the speaker at the same time, is my hope. That should work as long as it's a bigger chip. I'm gonna make another copy. So I might want to go back to that. We don't have source control here. Because we need to put this in a bigger chip because we need one more line of code, which is kind of bullshit, if you ask me. So we move 50 to P1 and we sleep for 1 second. Okay, P1 being our output here. So where can we fit this? P1 right there. Yes, I know pins aren't connected. Okay, so now how do we wire this? X0 can be the cry. So we've got them backwards now, but we can fix that in a sec. And now I suppose X1. Eesh. Okay, how do I make room for this? We can't move this any more to the right. We could move it 1 up. Nope, we can't do that either because we need all 3 of them going here. So I guess we have to move this to the left. I don't know, might as well move both of them. I just don't like doing that because it obscures the labels. So we had x0, x1. X0 is the lower one here. Oh, so that's fine. And now x1, let's wire it around this way so there's room for a bridge. And x1 can still connect to the top. Okay, the wires are connected. And now we just hope this works. Parts not sleeping blocked on read. Sleep for x1. Hold on. What do you mean not sleeping? The first command is to sleep. We're sleeping waiting for x1. There's no input yet. And we send 50 out. That's fine. And already we have an issue. So I guess we had to be in a sleep loop. This wait, not sleep x1, sorry. We need SLX. Wait for x1. SLX, wait for x1. There we go. Okay, well, something happened. Okay, let's look ahead until something interesting happens here. And here we finally are about to get a 1. So we move null to x1. So what's going to happen? Activating this chip here, or no, activating this top chip. So we do that. Oh, we did that. And then now this here is playing the giggle sounds. We're checking that 0. We jump back to play. Why is it playing 100? 100 is the first thing it's supposed to play. Cool. But this thing still has an output signal of 50. So I guess that kills that theory. I don't know. Maybe if I were first to set my output to 0. Move P1 to 0, then it wouldn't like override or something. Yeah, let's do that first. Move 0, 0 to P1. Well, it's still outputting 0. Okay, so we move 0 to our P1. Great, so there's no signal going. And then we move null to x1 and give it the go-ahead to do stuff. So our top chips should be working now, right? Great, it takes that. And then we move x0 to accumulator, it's 100. So we're not going to jump. We move the accumulator out, so we're going to move 100 out. Cool. That's good, right? That's what's supposed to be happening. Oh, and then we're jumping in a loop. We're forgetting to sleep between each jump. Oh, fuck. We need one more line. Okay, we can do this. We can remove this comment. and we can move this code up one line. So move 0. So after we move our accumulator to P1, we're going to sleep for 1 second. Okay. Let's try that again. And beautiful, beautiful. Okay, so we figured it out. If you're going to have multiple basic outputs going to the same thing, you need to turn off this output before you send a signal from something else. Otherwise, that 50 stays on the line here. So we'll do the same thing here on this other side. Move 0 to P1 before sending the signal to the other chip. And now the code in both of these chips is identical. And that should do it. We have ourselves a creepy doll. Oh, but we've forgotten to move things back to P50. So once it's all done, we move 50 to P1. Yeah. Hold up, what's going on here? So my baseline is 100, and then nothing happened for that second one because the baseline, our actual was 75. Do they like add? I just want to make another thing here just to see if chips add. So let's say we have 2 chips. They're both connected here. And this can be move 25 to P1 and then sleep for a second. And this one here is going to be move 75. And what happens in that case? Is it just constantly expected? Actual is 75. Does it become the higher one? Or is there like a race condition? If we swap these two around, let's make this 25. Okay, so it just becomes the higher one of the two. When there's a conflict, it becomes the higher one. Okay, that's good to know for future reference. That might come in handy when we're like golfing something later on. Okay, but what is going on here in this case? We end up somehow with a 75, which was the last value from here. Oh my god, coding with strangers. Hey, it's been a while. Good to see ya. Welcome, welcome. Welcome to the stream. What were you working on tonight? And do any of you have any interest in logic puzzles? Because I've got a puzzle for you, a little puzzle game. If you want to do a puzzle game while I'm doing a puzzle game. Yapping and doing some new stuff. Cool, cool. On the truth tellers one. Fair enough, fair enough. Well, you can kind of brute for like how many 3-word questions can you even ask? You could just list them all out and then I could analyze them for you. Okay, I've got a game. So you're on the game show now. I'll be the host. And we have 3 prizes. So there's prize A, prize B, prize C. Prize C isn't even really a prize. It's like a consolation trophy or whatever. Prize B is pretty good, but you want prize A. But here's how the show works. You make a statement to me. And if it's true, I get to choose between prize A and B to give to you. If your statement is false, I give you prize C. So, can you make a statement that forces me to give you prize A? Is the question here. Is it Tyler your brother? Well, so they're all triplets. So both of the Tyler and Taylor would answer honestly, they'd answer the same way. They would, and Frankie would say false. Well, Frankie would say no. So all that tells you is that like the person who just said no is Frankie, and you still can't tell Tyler apart from Taylor that way. Did Coding with Strangers radio last, true or false? That is very true. You win prize B. Congratulations. Meanwhile, I'm gonna stare at this and figure out how I fucked up. We've got a signal. Oh, this is Shenzhen I, by the way. It's a game. I have a CAD here. There's like a Chinese fabrication company that I'm working for. I'm role-playing someone who's like migrated to China to work there because I can't find an engineering job anymore. And they gave us all these designs, and we have to implement this. This one we're doing today is a creepy doll, a haunted doll, and it just randomly plays noises every now and then. So the noise I have stored in read-only memory here, and I read it out when I get the right signal from a random number generator. Oh, you're welcome. That's also a true statement, by the way, so you get another prize B. Now my problem is, once I move my last value out, it stays on. Crap. So once I'm done, I need to move 0. I need to move 0 to P1. Ugh, was splitting this between 3 chips a bad idea? Or in this way a bad idea? Maybe what I should be doing is sending this back over the X bus to this chip and letting this chip handle all of that because we've got more space down here. Yeah, then we don't have to do that nonsense. I'm gonna snip these 2 wires. Snip, snip. Okay. So we're gonna move our accumulator over X1. Well, here's the thing. We're gonna have to loop through that, and we're just gonna end up copy pasting this whole loop down here, which is kind of annoying. Because we still need a termination condition. This needs to know when to stop pulling from the loop. But if there's a way... Like, I wish I didn't have to move X1 to null. Because I need to do both these commands. I need to sleep. I need to move that to 1. You're still committed to your cheesy ABC answer. It's the best you've got. But it seems there's a more correct answer. Oh, sorry, your ABC answer? I missed that. What did you say? Oh, right. I will receive prize A, for which you will always ever get prize B, unless I'm feeling generous. Okay. I know exactly what needs to happen here. Oh, you know what? Here's what we're gonna do. This very final thing is a 0. We'll just move that 0 over to P1. That's fine. Then this one over here can overwrite it. So, yeah, we have a solution. Test equal act 0, jump done. Move act to P1. We're always going to move act to P1, even if it's a 0. And then, if it turned out that the thing we moved to P1 was a 0, we're going to jump to done and skip the sleeping step. Yeah, okay, that works. And I think that now my instinct is telling me that there's a way to golf this bit shorter here. Now that we've changed how that loop works. But yeah, okay, that does that. Oh, yikes. Okay, I fucked something up. What did we change here? We, if it is 0, we move jump to done. Let me just look at what we had before. Or let me jump to done. So previously we had what's here on the bottom. If it's 0, we jump to done immediately. Here, if it's 0, we first move it, and then we jump to done. What's the issue there? So it works fine at first. And then right here, it's already all wrong. Oh, right, we disconnected this. I forgot we snipped our cables. Oops. Okay, the cables are back together. Let's run this. There we go. Easy fix. Just wire the cables back together. Oh fuck, what happened here? Okay, we have a tiny bug for no good reason. Well, those are fun bugs. Well, crap. Okay. I need to pee. So I'll be right back, but I figure I could leave logic puzzles on while I'm off. Like 1 millimeter off. It's within tolerance. I know, right? Yeah, like that's. Am I playing? I don't know. I don't know what that's about. We'll figure it out. Maybe I just copied the numbers wrong. All right, I'm back. Um, okay, and what's going on here? It looks like the outputs are wrong on the second thing. So it worked the first time around. So this is 1, right? This is triggered by seeing 1 on the input. Simple input rent. Okay, great. This next one's going to be a 2, right? Okay, we see the 2 working correctly. Cool. Now the next time across, we have a 1, and then we have a 2. We get the 1. That works fine. We get the 2. And that is working fine. Okay, so maybe the issue is when you play the same thing twice in a row. So this is a 2. And then this is a 1. 2 and then a 1. What's working? 1. That's apparently working. Okay, what the fuck? This is the worst kind of bug. So it is stuck. The actual value is 42. 42 is coming from, oh, it's coming from the other chip, from the 2 chip. We never update our code here. Okay, that's it. I see. It flatlines to whatever the last value was from the other chip or something. To whatever the last value was. 42. That's this right here. The last value from the cry chip. Okay. Awesome. We got it. Our power usage is firmly average. Our lines of code is a lot, as is our production cost. Okay, so it seems like most people figured out a simpler way to do this. But this might be one of those I refactor next time. Here's the thing. Like, this code is identical in both cases. You can't really have a register as a variable. But like, you could have... Maybe I can optimize this right now. So you could have a chip that just sits between the... chooses one or the other of these two and passes it on to the big chip. Right? I want to see what costs people got. I think the ROM chips are each like $1. 15. Some people seem to have done it in, is that 10? 9? 9. So that's 6 yuan cheaper. They did it in just one big chip then. Is that right? And how much does it tell me the cost of these? No, I can't look at it there. Costs are here on the side. So my ROM chip costs 2. I have to have 2 of those. Maybe we can do it with just the big chip. But if you're doing it with the big chip, you still have to choose between X0 and X1. I need like some sort of multiplexer. Right, if all this code here was generic and was attached to a chip that just chose between those two, then we would still have two chips, but like we could do that. Where this always just read from X0 and then another chip was just choosing between the two ROMs. That chip could be this chip here. But that feels... See, when you put one chip in a loop and another chip in a, like... Well, they'll both end up with lots of code. Well, maybe I can start by... shrinking this code. Which I think I can do now. So after the jump, we sleep for 1 second. So we need the jump to happen before the sleep, so that do we need it to happen before the sleep? I think we actually need to. I don't think we need to, so let's jump to done. Okay, no, yeah, we do need it. Because what then happens, it's still outputting the 0. Right, because the done, the move null to x1 needs to happen sooner. Well, let's at least turn in that work and see what this thing. Haha, it worked, kind of. Someone posted their haunted doll being haunted, and it was starting to gain some attention, but very soon afterwards they opened up the doll and found the mechanisms. The mystery was solved pretty quickly. Well, that's lame. But they still don't know where it came from, and I believe that Ghost Electronics have a potential very bright future in the marketplace. We could even build them during ghost shifts at our assembly lines. I will continue to research the possibilities. Okay, stop it right now. I forbid you from doing anything further relating to Ghost Electronics. And he backs down because he knows he's unhinged. Oh, jeez. Now here's a question. How many of these were, like, deployed? They didn't fall for it. First thing they thought to do was open it up. I think I'll save optimizing this for like my warm-up next stream. Because I think I can do that perhaps in one chip. One big chip. But yeah. Yeah. Definitely not my finest work there. The kid knows how to reverse engineer. I guess they didn't really need to know how to reverse engineer it. They just needed to crack it open and see that, oh, there's chips in here. There's not supposed to be electronics installed. Are we already selling normal dolls? Is that what happened? Like, are we an electronics company that sells normal dolls and decided to put some haunted chips in some of them? Hey. Okay. We'll take a peek at one more. Because I'm gonna need sleep here soon. But if it's custom specifications. Oh, this is another upload a custom specification to the Steam shop. Oh, okay. Ever wonder where the specs you test against come from? Well, we use a little program called Concept Spec to generate them. I figure you're ready to create your own specs if you want, so I put a link on your desktop. Concept Spec isn't exactly the most elegant program, but it'll do since, you know, there's no choice. Just remember that Good specifications result in good designs. Poor specifications result in poor designs. That's not. I've seen plenty of good specifications resulting in poor designs. Fair enough, like my previous one. I mean, honestly, my design was at least readable, right? It was expensive and used a lot of lines of code, but it was readable, I hope. Yeah, so this new thing appeared on my desktop here, concept spec. Um, and if you browse the workshop, it opens you to the Steam community page where these are. And otherwise, you can just create new specs. Um, and I don't know how it works. Like, keypad, it's always going to be a keypad? I don't know how we change things there. But anyway, I'll look into that sometime. Um, I think I'm gonna end by showing you some more of this book because there is a project that this ties to, and I won't keep you hanging on on the puzzles here. But okay, so maybe I shouldn't have skipped this question number two because it does kind of relate to everything else that comes later. So there's a question I could ask you that has a definite correct answer, either yes or no, but it's impossible for you to give the correct answer. You might know what it is, but you can't give it. Can you figure out what question I could have in mind? So I could ask you, is your answer to this question no? Right? If you said no, well then that's false because your answer to the question was yes, but yada yada. If you said yes, then that's also false because your answer to the question wasn't no. Um, but it goes in a loop. Am I explaining that properly? So if I say no, my answer to this question is not no. Well, that's a false statement. So I can't answer it truthfully. And the reason that works is because of self-reference. Self-reference is a theme in a lot of these puzzles. The same with the three prizes. So here, what you could say, are you okay with spoilers? You know, I think you are. What you could say here is, uh, what could you say? You will not give me prize B. And if I gave you prize C, then then that is true that you did not give me prize B, and that's a false statement. And like my statement was true, so you can't give me prize C because the statement was true. So the only way to keep my statement true is by giving me prize A, right? Because if you give me prize C, it becomes a true thing, and you can only give prize C when it's a. I'll let you think about that. But it gets harder. There's a fourth prize, um, and now you actually do want prize C. You like prize C better than the other prizes. So for A and B, you get if you say something that's true, you get A or B. If you say something that's false, you get C or D. And now how do you get prize C? Or you could say something altogether that makes it so I can't give you a prize. You could say you're gonna give me a booby prize. You're gonna give me prize C or D. You're basically saying um, this statement is false. And I'll spoil you on the first of the John James and Williams. Yeah. So John James Williams. I changed the names so I could have true, true, and false. But here in this case, you could say are okay. We're trying to find James. You could say, "Are you James?" Um, And James would answer true, William would answer true, but John would answer false. So the trick here, since you're trying to find John, you try to find a question that both James and Williams will answer the same way. And one such question is, are you James? Because William will lie and say yes, James will tell the truth and say yes, but John will say no. Still saying the truth, but say no. And the thing that we've done here when we ask, are you James, is that we've distinguished between John and James by asking a question that those two answer differently. So there's actually two things I'm doing here. I'm asking a question that James and William answer the same, right? And I'm also asking a question that John and James answer differently. So you could get to the solution by thinking of either of those kind of pairs. Um, there's a variant of this puzzle. If you get the solution to one, then two is a good homework puzzle here. What if John and James were actually liars? Wait, is that the original? Yeah, the original is that John and James are liars. Okay, so what I just solved for you is two, actually, where John and James are both truthful. So what if they were actually liars? What question can you ask? And you can do something very similar. And the answer to this puzzle is fun. It's interesting. And then we have more puzzles with twins here. But I want to show you I want to skip ahead a little bit. Oh, here's something very useful. Zuno, you might like this. This will help with a lot of truth teller puzzles in the future, and it's called the Nelson Goodman principle. So basically, anytime you have a truth teller and liar puzzle, like the two guards at the gates or whatever it is, um, all you have to do is instead of asking, let's say you want to ask P, ask if P is true. You could instead ask, what would you say? Would you say that P is true if I asked you? And now the liar kind of double lies, right? So the liar lies about saying the lie, and then the liar tells you the truth. So that turns a liar into someone that's straightforward because you're asking them like a double negative question. The truth teller, it didn't matter. Sat solvers for the win. So here's the thing: I don't want to do this with a sat solver. So I don't want to do this with logic programming. I don't want to do it with a solver. What I want to do this with, three-word questions? No. So like the Nelson Goodman principle is just like a general principle. But you could use that to help you find, like you could use that to help you find a question that works or like a statement that, yeah, a question that works. And then once you have a question that works very easily, all you have to do is like negate it or like add in the self-reference. Then you can try and figure out a three-word question that still works. Um, yeah, I don't want to do this with logic program. I don't want to do this with set solver. I want to do this with a theorem prover. And a theorem prover is pretty well like okay, like you can make a program that like gets you the right answer in some way. But I think this is well suited for a theorem prover because you're kind of well, you're actually making a proof. You're actually baking your understanding of the puzzle into your solution. Right, like when you read the sat solver, you're just reading, okay, like this is brute force basically, and here's the answer. But when you read the solution from a theorem prover, what you're seeing is like this is why the answer has to work, right? You're like feeding in like this is what I know about this. You model the problem, and then you like wire it all together. And like in choosing, so I want to do this with Lean 4. I also looked at some other. I basically went to ChatGPT and said like, "Hey, solve some example problems here using these languages." And I like the results best from Lean 4. It's like a little bit more verbose, but like it's explicit. And since I'm gonna be learning theorem provers, like I'd like to use this as an example because it can Like while I'm coding, I'm also like sharing the way that I think about the puzzles, right? No, Isabel. Yeah. So Isabel solves this too easily. And that's it. Like that's part of the issue there. Like I want the proof to be in there. In fact, let me see if I can pull up some code that compares Isabel and Isabel's written in Scala, by the way. Did you know that? Partially in Scala, I think. Okay, so here I have some code comparing Isabel and Lean. So there's like a whole class of puzzles called. Well, I'll get to Isabel and Lean in a second, but there's a whole class of puzzles called like knight and knave puzzles, where the knights are the truth tellers and then the knaves are the liars. So this goes through yada yada. There's a lot of like there are a bunch of puzzles with Arthur and his twin brother where you don't know his name, and there's some fun puzzles here where like this logician married married someone but forgets their name and doesn't know if they are the truth teller or the liar, the twin. So a lot of like fun little questions come out of that. And like these are all like fun logic puzzles, but they're all warm ups. So even this is warm ups. Yada yada. Um, we've got like a few chapters here on knights and knaves. Let me pull up, including like my favorite logic puzzle of all time, which I'm gonna skip to that and share this with you because this is gnarly. This is really cool. Um, okay, in search of the fountain of youth. So I'll share some of the context here. Uh, so Arthur Reynolds, Esquire, was in search of a recipe for immortality. He had a great deal of occult and alchemical literature, but could find nothing of practical value. Then he heard of a great sage of the East who was reputed to be a specialist in this area. At great expense, he made a lengthy journey and finally found the sage. Is it really possible to live forever? Oh, okay. This is this is needless backstory, but we'll take the joke. Is it really possible to live forever? He asked the sage. Oh, quite easily, replied the sage, provided you do just two things. What are the two things? First of all, you must never make false statements. In fact, you must resolve to make only true statements from now on. That's a small price to pay for immortality, isn't it? Oh, definitely, says Raymond. Well, about the second thing? The second thing is that you say now, I'll repeat the statement tomorrow. If you do just those two things, then I guarantee you will live forever. Which is true. Which is true. Um, it's a cop out because you can't force yourself to tell the truth about something that's about to happen. But again, this is another like um, self-reference in that logic puzzle. Um, anyway, Reynolds thought about this for a bit. Oh, of course. If I do those things, then I'll certainly live forever. Because if I truthfully say now, I will repeat the sentence tomorrow. Then tomorrow I will again say I'll repeat this sentence tomorrow. Then I'm truthful tomorrow. Then I'll say the same thing again the next day, so forth. Exactly. But the solution is not a practical one, protested Reynolds. How can I truthfully say that I will do something tomorrow if I don't know for sure I'll even be alive tomorrow? Oh, you want a practical solution, said the sage. I didn't realize that. No, I'm not very good at practical solutions. I deal mainly with theory, but practical solution. The only thing, um, I promise we're getting to the puzzle here in a sec. The only thing I can think of is a fountain of youth. Have you considered searching for it? The fountain of youth, cried Reynolds incredulously. Why, I've read about it in history books, and I know that many have sought it, but does it exist in reality or only in the imagination? That I do not know, replied the sage, but if it does exist, I know as likely a place as any where it can be found. What place is that? Asked Reynolds. The island of knights and knaves, replied the sage. I cannot guarantee the fountain is there, But if it is anywhere, the island is as likely a place as any. Okay, technically true. As likely as any is a cop out. But anyway, Reynolds thanked the sage and departed for the island of knights and knaves. So the island of knights and knaves is full of knights and knaves. Everyone there either always tells the truth or always tells a lie. And the last three chapters, like the last three sections of this book, were all about people on that truth teller island. So chapter 5, 6, 7, 8, four whole chapters on these kind of puzzles. But this is grand finale of all of them. And here, let me center this so that I'm not blocking it. Two columns, single column. Uh, we want some wide margins. Okay, that works. Um, okay, so here we are, a grand meta puzzle. This is my favorite logic puzzle of all time. Um, and you don't even have to solve it for it to be your favorite. It's just gnarly in the way it's phrased. So Reynolds' next adventure is far more interesting. It involves as profound a logic puzzle as any I have ever come across. On the following day, Reynolds came across two natives, A and B, and said to them, whoops, I lost it trying to mess with my margins. Okay, Reynolds came across two natives, A and B, and said to them, please tell me whatever you know about the Fountain of Youth. Is it on the island? The two natives then made the following statements. If B is a knave, then the Fountain of Youth is on this island. Then B said, I never claimed that the Fountain of Youth is not on this island. Okay, so Reynolds thought about this for a bit and said, please, now I want a definite answer. Is the Fountain of Youth on this island? One of the two answered. He either said yes or he said no, and then Reynolds knew whether or not the Fountain of Youth was on the island. So some months later, Reynolds told the above facts to Inspector Craig. He is a good friend of Craig's, and he knew of his fondness for logic puzzles. Craig said, it is obviously impossible for me to deduce from the facts that you've given me whether or not the Fountain of Youth is on this island. You haven't told me whether A or B was the one who answered your second question, or what he gave. Whichever one it was who answered, suppose the other one had answered instead. Do you know if you could have decided, if you could then have decided whether or not the fountain is on the island? Reynolds thought about this and finally told Craig whether or not he knew whether he could have decided had the other one answered the second question instead. Thank you, said Craig. I now know whether or not the Fountain of Youth is on the island. And now, from that, we're to deduce, is the Fountain of Youth on the island? So this is great. Right, like obviously, from the first bit here, I'll go back to statements. A says, if B is a knave, then the Fountain of Youth is on this island. And B says, I never claimed that the Fountain of Youth is not on the island. That's obviously not enough information for anyone, but Reynolds was able to ask a question that gave a definite answer. And then, like that's a little bit of information, but it still doesn't tell us, right? And then Reynolds then tells Craig whether or not he would have been able to deduce it if the other person had answered instead. And given that Craig finally knew, now we're supposed to know. And the thing with a lot of these logic puzzles, when you're trying to figure out like the answer to whatever question is you're answering, you might not figure out who is a truth teller or who is a liar. So in this case, like you might not even be able to deduce um, after going through this whole puzzle, you might not even be able to deduce like which of A and B was a truth teller or which of A or B Reynolds asked a question to, asked the follow up question to, or like what the question was. Oh, actually, no, no. What the question was just this: Is the fountain of youth on the island? So that's the second question. But yeah, one of the two answered. We won't know. We won't necessarily figure out who answered, and we won't necessarily figure out whether they said yes or no. Actually, we might figure it out. Um, but knowing that we we might not figure out any of these other bits, like um if answering the other, or if the other person answering would have told whatever. We might not necessarily figure out those all things, but we can figure out if the Fountain of Youth is on the island. Um, so very cool, very fun to solve that one. And by the time you get to this point, you're well trained and you should be able to solve it. Yeah, yeah, exactly. And that's one of the things that's so cool about this puzzle. And I would love to model this in a theorem prover and like prove it for sure. Oh, this is To Mock a Mockingbird. So my favorite puzzle book, and it's my favorite not just because of this. So this is a really cool puzzle, but this goes on. Oh, there's a solution. If you want the solution, you can come back to the stream and you can pause those pages there. Um, but that so all that we've looked at so far has just been. Let me look at the table of contents. The first two parts of the book. So the first two parts of the book are like standard logic puzzles, standard looking logic puzzles, but they have a theme in here, which is that they all kind of involve some sort of a self-reference. And then the last four parts of the book, so parts 3 through 6, are actually all about these mockingbirds. So a mockingbird, um, if you so let's take a mockingbird A or something. If you give the mockingbird the name of any bird, it will respond with the call of some other bird, right? So these mockingbirds are kind of like functions. You give it, like we'll let the book speak for itself. Given any birds A and B, if you call out the name of B to A will respond by calling out the name of some bird to any kind of bird, right? So these are functions that like evaluate to other functions, sort of, right? And the thing is, and then there's a special bird in this forest here. So there's a mockingbird. So there's a bird M such that for any bird X, the following condition holds. Flip page. MX gives XX, which is to say that M's response to bird X would be X's response to hearing its own name. And just the existence of this mockingbird changes a lot of weird things in the forest. It makes a lot of things possible. Um, so this allows for a fixed point to exist. And these mockingbirds are secretly combinators. So it's like the lambda calculus without the bound variables. Um, there's probably a better way to sell combinatory logic here. It's not just lambda calculus without bound variables. I'll think on that for a bit. Um, but anyway, like you can go on, like if you've heard of the Y Combinator, like the Y Combinator pops up in here, and like you might have even implemented in Lisp or something, but you can also implement it straight up with just combinators. Is this where all the combinatory bird names come from? Um, yes, no, no, not really. There's he's so like this author's a mathematician. He's hiding the fact that this is about combinatorial logic. But it's really cool because like this whole book is actually just teaching you math, but it's like teaching the whole thing to you through logic puzzles that get like progressively harder and harder. I did a primer once on combinatorial logic. It's on my GitHub. Um, St squared GitHub combinatory. Yeah, and then I used to host puzzle nights, and I presented this as a puzzle one night. Basically, use combinatorial logic to implement something like XOR. So that's a fun little exercise. It take like an hour or something. But yeah, this is Turing complete. You can implement the numbers with this. You can implement you can implement NAND. You can build a whole computer on top of this, and I think that's very cool. So these birds, these birds, if you include the mockingbird, are Turing complete. 404 private repo. Oh, I guess that is a private repo. Let's see on my public GitHub. GitHub, oh, GitHub's G squared. Okay, there's this. I have a gist. And this isn't like this is old. It's not the way I present it now. Yeah, S and K are Turing complete. And in fact, you can just do it like there's SKI. There's a combinator. What's the combinator? B. You can implement S and K and I all in terms of just one combinator B. So you could actually do it with just one. That's all. Kind of like how a computer you can build it with just NAND and faults. Like that's enough for you to get all the other gates and all the other logic. You can do just a single combinator is Turing complete. And it used to be the case that in Scala 2 you could implement the SKI combinators in the type system and have Turing complete computation in the type system itself. But they no longer allow that in Scala 3. They wanted to fix things and make it you can still do a lot of gnarly things in the type system, but it's no longer Turing complete, I think. But yeah, I'd like to go through this book one day using Lean 4. And the reason I want to use Lean 4 rather than where is that? Did I pull it out? You don't think it's B? B is function composition if you recall correctly. Yeah, I'm forgetting. It's been a while. This combinatorial logic thing that I sent you is like 10 years old. It's been a while since I've touched it, but I want to revisit it, like in the context of this. But there is a combinator such that like you can compose all the others from just that. Um, so here's the thing about combinatorial logic: like you can implement calculus, the lambda calculus, in terms of combinatorial logic. So it's kind of like a lower level assembly language where variable binding has been like compiled away, and it's only done in terms of combinators, right? So if you like just erase all of the names, you can just do it all with structure instead. And like that could be your virtual machine on top of which you implement a language like a lazy language like Haskell. You could actually I think you could actually do it that way. I also have a book in my library called Compiling Functional Languages that implements like a lazy Lisp in terms of combinatorial logic. So like that's possible to do. Like you use graph reduction. It's kind of like the spineless tagless G machine that is used in Haskell. Like you're doing graph reduction to implement the language, but you're doing it in terms of combinatorial logic. Yeah, if someone could look up what that combinator is that you can implement the others in terms of, I'd like to remember that. Okay, so here I was doing a little exploration. Okay, so I asked ChatGPT about some of these knight and knave puzzles, and I asked to do it. I should show you what puzzles I'm actually talking about. Yeah, let's go to that first. Some unusual knights and knaves. Okay, here. So there's some questions here. Is it possible for any inhabitant of this island to claim that he is a knave? Um, and in this case, that should be false, right? Because no knave could claim that, because they'd be telling the truth, and knaves don't tell the truth. And no knight could claim that because they knights don't lie, and that would be a lie. But there's these like questions to think about, and I used them as an example. So here's what that looks like in Lean 4. Um, and like keep in mind, I don't program. Like I've started reading the Lean book yet, but I don't program in Lean. But there are propositions. So here, a knight is someone. So you have a person that makes a proposition, right? A knave is someone that is not a knight. So the proposition here isn't necessarily true or false. Um, so variable truth for all p says p. Okay, so given some proposition, the knight will always um, say that proposition. But if something, but like something a knave said is going to be false. So here's a translation here. If I'm a knave, if I'm a knave, the knight P, um, if P says I'm a knave. So theorem Q1, given a person which is a knight or a knave. So says P, knave, and given that knight is equal to knight. Okay, right. So we can't say this statement here that they said this needs to be false, and we prove it by this statement here. And then this is your proof. And then this is what it looks like in Isabel. And I know nothing about Isabel. But looking through these, I was liking that the lean four was more explicit. So here the proof forces you to articulate why A can't be a knight, how A how this is being used, etc. Where that's not necessarily true here. So at some point you just use simp, and simp does the solving for you. So once I learn lean four, I'll take a look at doing some of these puzzles in using it. But I don't know, like they have some similarities, like where you model them seems similar. It's just where you're proving them, you have to be explicit in lean. Whereas in Isabel, you can just have it solve it for you. Yeah, maybe. I don't know. Like I don't know lean well enough, but this is like enough of a preview for me to be like, okay, well, given how these two work, I think I'd rather do lean four. I had other reasons for wanting to learn lean. It's been on my list for a while anyway. Um, like I want to mix it in with like some programming too, and it's like a nice balance between like you can actually do functional programming in lean four, and not just. Would you mind increase the font size thing? Uh, Too late. Sorry about that. Um, but yeah. Anyway, that's my logic there. That's why I'm thinking, and that's why I want to do some of these in Lean Four, and that's why I want to do. Most importantly, like that's why I want to use a theorem prover rather than just a logic programming language, because I don't want to just like brute force and have it spit out the answer given like whatever constraints I modeled. I want to have to like prove it. Fair enough. Yeah, okay. The logic reasoning puzzles, the LLMs. Yeah, absolutely. If you Here's the thing. Um, the reason I asked it to use, so I've taken some puzzles from this book. You can't really trust ChatGPT. I've taken some puzzles in this book and asked ChatGPT, and it just completely confabulates an answer. Um, it cannot solve these logic puzzles. And I'll go and I'll be like, no, this is a solution. Let me explain you why. And they're like, oh yes, I see why. And then I'll tell it, oh, I was lying to you, by the way, blah blah blah. And they're like, oh, I see you were lying to me. So the answer is actually blah blah. It just confabulates every single time. It doesn't even know enough to know that it doesn't know it, right? So you can't trust that. Um, I don't know if I trust the code that I was just looking at from ChatGPT. Um, but I I see the syntax, and I see the use of simp in Isabel, and I'm like, what, I can do that simp. I like how explicit this is. I'd rather be explicit as I'm running through this. Uh, like both for myself and for the reader of the code. Um, really get it out there. IOTA might have been the combinator I was looking for. Yeah. Okay, let's look that up. IOTA combinator. IOTA and JOT. Oh, it's done as as an SOLang. Right, logic. Oh, maybe it's in here. Iota x is a basis 2. 1 point basis. So x where x is basically that. So that gives us k, and that gives us s. Oh, let me make that bigger here. Sorry about that. Um, a 1 point basis. The IOTA programming language uses X as its sole combinator. uh, okay, and from there, you can give yourself K and S by defining them in terms of X. Um, and here's another example of that. Okay, there are multiple. There are multiple one-point bases. Common is B and C. Okay, there are alternatives. I think in the puzzle that I sent you from my GitHub, it is there are 6 combinators I'm using there. So SKI and then BK and something else. On mechanizing the meta theory of lean. Oh, that's cool. I should look that up. Let me look that up while I'm here, actually, so I have it in my tabs. Yeah, absolutely. Okay, let's uh, lean mechanizing meta theory. Oh, okay, cool. I'll give that a watch later. And yeah, I'll share the link with other people too. Iota and Jot. Iota and Jot are languages with extremely minimal. Okay. Anyway, whole programming language based on it. That'd be gnarly to write in that way. So the cool thing I sent you about that combinatorial logic puzzle, like you write at the end of it, you basically you write XOR, and you see it implemented in terms of combinators and just like this big old string of combinators, and you see it working and actually like being able to give you true or false, and it's cool. It's cool to see like that big batch of combinators actually doing general logic. Um, I know, like in CS, every time that happens, it's exciting, right? When you have a NAND gate and faults, and from there you're able to construct like all the other gates, construct XOR, or when you have types, when you do that in your type system and are able to make XOR in the type system, etc. Anytime you're like getting to that point, even getting to just and, well, maybe not just and, getting to that point is always exciting because there are like a lot of ways to get there, and it's just cool to see how many different ways you can um, make things turn complete. And like once you get that proof, oh look, I implement XOR. It's always exciting. So maybe one day I'll revisit that combinatorial logic puzzle as a side project because I it can be solved in about an hour. So maybe I'll demonstrate that. Anyway, it is time, like the amino acids of code. Yeah, exactly. It's time to find a raid. I don't know why I can't. Okay, there we go. So let's do that. Can I relink the puzzle? Oh yeah, absolutely. Give me 1 sec. If you forget, it's always on my GitHub too. To GitHub. Um, so this is as a gist. Maybe that's not the best way to share it. I think I have this set up as a repository. Actually, I have a better link for this because I have this set up as a repository. Oh, well, thank you. I'm glad you like being here, Carstring. And welcome, welcome. This is my first time seeing you, I think. Okay, hold on. In my repos somewhere. Uh SPN combinatorial logic. So no. We just want my GitHub repositories, combinatory. Here we go. SPN combinatory logic. So this is where it's phrased as a proper puzzle. So here I give you a cheat sheet. Um, I link you to a website, which I hope is not dead. Okay, great. It tells you about bracket abstraction algorithms. Okay, this here gives you everything you need. Oh, the Ginger Dev. Thank you. Welcome, welcome. All right. Yeah, this gives you everything you need to prove that these combinators are Turing complete. And I even have I have tests in here. I don't know if this project will run because it's so old. This is 11 years old. But I have tests that go where is it? So you're supposed to uncomment these tests as you go. So see that you're able to implement basic reduction, basic combinators, etc. I could probably rewrite this and make it. Maybe I'll rewrite this one day and make this more accessible. But you uncomment these as you go until you get reduction, and then you implement bracket abstraction, and then you implement true and false. And by the end, I'm asking to implement not, and, or. And here's the thing, not here is just a term. It's a term like anything else. It's like a sequence of combinators that are multiplied together. I don't think yeah, once you have not, and, or, that gives you enough to make XOR if you wanted. And I don't know, like seeing these tests pass is exciting. It's a good experience. Oh, sorry, that is not big enough here. Yeah, this is like this is the finale. You get not, and, or. That's enough to give you XOR. And these are the tests. They're like simple, but like it's exciting to get to that point where like, oh, I was finally able to implement and in terms of SK and I. So my goal is to walk you through. Did I share that? Yeah, but maybe I'll rewrite this one day in a way that's more accessible than having to run an 11-year-old Scala project. I hope SBT just runs that all right. But yeah, time to dust it off. I know, yeah, if I'm gonna be doing this kind of project on stream. Okay, so let's look for a raid. Ginger Dev, I stream when you're asleep. It must be from across the pond, as they say. Um, okay, I can't promise I'll raid you, but you know what? I'll at least take a look at your stream. Ginger Dev. And what are you working on? You are doing some game dev? All hail the orb development. Okay. But I do want to check what else is out here. Um, uh, we haven't been to Sergeant Pepper in a while. Bunny bites. Okay, there are people I know, but I'm hoping for maybe someone doing Deadly Towers disassembly. Okay, I really like seeing reverse engineering, and that's kind of on theme with stuff we've been doing. So this could be a maybe here. Let's take a peek. Drugs, intoxication, side effects of tobacco use. I think we're fine with that. Okay, yep, we've got assembly. We've got this assembly. I think this is what we want here. Yeah, that's pretty cool. We will enjoy that. Oh, geez. Here's a problem. If I enter the stream, I'm not gonna go to sleep until 5 a.m. Okay. But we'll send it right here. Where Oh, what is going on to my All right. Well, thanks for everyone for stopping by. I'll be back again next Monday, every Monday at 11 p.m. Eastern. It's Xkeeper, Ollie DBG. I'm not Oh, wait. No, I'm not familiar with Ollie DBG. Yeah, absolutely. I enjoy the puzzles. I'll always have more to fire off. Alrighty. Yes, Windows Debugger. Oh, okay, cool. Makes sense. All right, have fun. This will be a fun stream, I think.